In this video, we're looking at the common ion effect in section 3.3. So on the bottom of the previous page, we said that if a solution has the same ion as one of the ions in a dissolving compound, we call that the common ion. And the effect it has on the solubility is called the common ion effect. So in this example, we have calcium hydroxide and we are adding it to a 0.15 molar sodium hydroxide solution. First thing, write the equation for the dissolution of calcium hydroxide. So we are writing the reaction. Here's calcium hydroxide. It is a solid. Dissolution means dissolving. And if we look here, there is one calcium ion, aqueous, and there are two hydroxide ions, which is also aqueous. And that's our dissolution equation. Next question is calculate the molar solubility of calcium hydroxide in the NaOH solution. So molar solubility, we are looking for S. What is S? To find S, we set up an ice chart. So the initial, the change, and the equilibrium. So initially, we have a solution of sodium hydroxide. There is no calcium hydroxide in it. There are no calcium ions. There are some hydroxides. 0.15 molar sodium hydroxide has 0.15 molar hydroxide. As far as the change goes, we are going to be decreasing the reactants and increasing the products. Something important is this S right here. It's a solid. Solid, remember, stay out of the equilibrium expression. So we're just looking at the products here. So the calcium is a product in this reaction, and it is going to be increasing. Increases by the coefficient 1 times S, the molar solubility. And that's what we're looking for. The change for the hydroxide, it's positive because the product coefficient is 2 and times the molar solubility. So our equilibrium values, calcium is S and hydroxide is 0.15 plus 2 times S. So we're going to use the equilibrium expression to figure out the molar solubility, just like we've been doing for the past several examples. So KSP equals concentration of calcium ions to the first power times the concentration of hydroxide ions to the second power. So we can fill in some numbers. First thing, we know the KSP. It's not given in this exact question, but this is pretty common in the AP exam. So it's not right here, but you need it and you have access to it. If you look back one page, we've been working with this reaction for a while. So a lot of times what you have to do in the AP style is go back a question or two or three and find the information you need. In this case, the information we need is the KSP for calcium hydroxide. It's 1.3 times 10 to the minus 6 power. So this is our equilibrium, and calcium at equilibrium is S, and hydroxide at equilibrium is 0.15 plus 2s, and that quantity is squared. Now take a look at this, and you can see that this is going to get out of hand pretty quickly. You're going to have something where it's 4s squared plus 0.3s plus 0.3s plus, and it's going to get out of hand, and then you're going to multiply everything by s. That is going to be nearly impossible without a graphing calculator. So in chemistry, there is a very nice shortcut, and this is one that you're not going to want to skip over. You need to remember this shortcut. So we're going to make an assumption here. So look, the KSP, this is a pretty small number. If you really think about this KSP, it's 0.12345. This is the number. And on a scale of 0 to 1, this is really close to 0 and not very close to 1. And so that's the premise that we're going to operate on. We're going to make an assumption. Assume that 0.15 is a lot greater than 2s. Because it is. If you compare these numbers, 0.15, and our s is probably going to be something in the range of times 10 to the minus 4, minus 5, minus 6, minus 7. That's a huge difference. So here's the jump that we're going to make. If 2s is so much smaller than 0.15, then we're going to just say 2s is 0. We're going to knock it out of this equation basically. So here's what I'm going to do. I'm just going to say, since this is so much smaller than 0.15, if I add 2s to 0.15, it's still going to round to 0.15. Disappear. And this makes our math a whole lot simpler. We're not going to deal with polynomial expressions or anything like that. Now what we have is, there's our KSP, and it equals 0.0225 times s. That's 0.15 squared times s. Now this math is not going to be difficult. Divide both sides, and we find that s equals 5.8 times 10 to the minus 5th molar. We found our value for s. This is what we were looking for. Now, if you're really a stickler for math and this little shortcut really bothers you, let me show you how it works out. So let's go back to, you don't need to write this part down if you don't want to. I'm just going to prove to you that this whole thing works. I'm going to use a different color. So 1.3 times 10 to the minus 6th equals the s that we found, 5.8 times 10 to the minus 5th times 0.15 plus 2 times 5 minus 10 to the minus 5th. All of this is squared. This is 2.25. Let's go far with it. 348 times 10 to the minus 2nd. If if you multiply these two numbers together, you get 1.3070 times 10 to the minus 6. And yeah, these numbers aren't exactly the same, but take a look back at everything we've done. It resulted in two significant figures. If we round this to two significant figures, we end up with 1.3 times 10 to the minus 6th. And so this shortcut works. And so we're going to stick with this shortcut because it will save you lots of time and lots of grief as you go through these questions. So compare the solubility of calcium hydroxide in pure water with that of calcium hydroxide in the sodium hydroxide solution. And so if you're going to look at calcium hydroxide in pure water, really all we have to do is use our KSP expression. And let's see, here's our number, 1.3 times 10 to the minus 6th. And remember, this would be S in pure water, and this would be 2S squared. This is something we did in example number 1. And that is 4S cubed. And we did this, it was 6.9 times 10 to the minus 3 molar. And so if you compare these numbers, (6.9 times 10 to the minus 3rd is greater than 5.8 times 10 to the minus 5th. So that common ion in the sodium hydroxide solution is decreasing the solubility. Without the extra hydroxide here, the solubility is much higher. Looking at example 3, what is the solubility of lead to chloride in 0.10 molar sodium chloride solution? And we get the KSP in this question. It is 1.6 times 10 to the minus 5th power. Everything in this example goes like it did in the last example. So this one does not ask us to provide the dissolution equation, but it implies here that we have it. We need it, and so we need to write it down. PbCl2 solid, it's going to give us lead 2 plus and 2 chlorides. Let's use our ice chart here. Some things that we know. Lead 2 chloride is a solid, stay at an equilibrium equation. Lead. There's no lead in this solution originally, so this one's 0. There is some chloride to start with. There's 0.10 molar sodium chloride, which means there's 0.1 molar chloride. These are products. They're going to be ions entering the solution. This one is going to go up by 1 times S. Chloride goes up by 2 times S, the molar solubility. At equilibrium, concentration of lead 2 is S, the molar solubility. Equilibrium concentration of chloride is 0.10 plus 2 times the molar solubility. So let's write our equilibrium expression, KSP. Here's my lead 2. Here's my chlorides, which are squared. We have KSP, 1.6 times 10 to the minus 5th. We know lead is S, and we know the chloride is 0.10 plus 2S, and that whole quantity is squared. Remember what we did last time? We made an assumption. We're going to assume that 2S is a whole lot smaller than 0.1, which means we can just assume 2S is really close to 0. Which means when I come back over here, rather than solving for S cubed plus S squared, all that stuff, gone. And this makes it a lot easier. So if you were to solve for this, we would end up with S equals, and we find 1.6 times 10 to the minus 3rd. S is the molar solubility. It's a concentration. It has units molar. Calculate the solubility of lead 2 chloride in pure water and compare. So this is the same 1.6 times 10 to the minus 5th. We have S for the lead in pure water. I'm not writing out all the work. In pure water, we would have, it would be this without the 0.1, so it'd just be 2S. And that quantity is squared. So that's 4S cubed. And so we find 0.016 molar. So which number is larger? It would actually help if I wrote this in scientific notation. 1.6 times 10 to the minus 2, which is bigger than 1.6 times 10 to the minus 3. And so the one in pure water has a better solubility than the one that already has a common ion. In example 4, we have 6 compounds listed, and it says which of the following salts would be more soluble in an acidic solution. And so here are the options: zinc carbonate, barium fluoride, silver chloride, calcium phosphate, lead iodide, and magnesium hydroxide. So I'm going to circle the ones that are more soluble in the acidic solution. I'll give you a very quick overview and then we're going to move on. We won't spend too much time on this. So which ones would be more soluble in an acidic solution? Okay, so these are the ones. It says come up with a rule to quickly determine how you can tell. says salts with anions of weak acids are more soluble in acidic solutions. And again, we haven't talked about weak acids since Chem 1. Basically, with a weak acid, what happens is, here's your acid, and you don't need to write all this down. And here's your ions. A weak acid really favors this side. So maybe only 1% or 10% of it actually dissolves to become these. And so we have a K value that is really pretty small, like the ones we've been talking about. And so in general, these are favored. And so what happens is, if you have a salt with an anion that is in common with the weak acid, that would be this one. When you dissolve it, the reaction will shift this way, and it absorbs the stress on the system pretty easily. As far as the actual weak acids that go with these, you've got carbonic acid. It's a weak acid. Hydrofluoric acid is a weak acid. Phosphoric acid is weak. And the magnesium hydroxide is a little bit weird, because in an acidic solution, the hydroxide is going to be reacting with hydrogen, like we saw a few examples ago. And so it worked completely differently. But if you're going with the whole weak acid idea, the weak acid here would be water, and we'll just leave that alone until we get to acids and bases. The ones with the strong acids, AgCl, its strong acid is HCl. PBI, hydroiodic acid. When it comes time, we will memorize the strong acids. There are only 7 or 8 strong acids. So if you remember those, then every other acid has to be a weak acid, and it makes this sort of thing a little easier. In example 5, we're talking about selective precipitation. So consider a solution that contains calcium ions and lead ions, both at 0.010 molar. If a solid sodium sulfate is slowly added to solution, which one precipitates first? What is the concentration of the first ion that precipitates when the second salt begins to precipitate? A lot of stuff here. Let's try to keep it focused and go one step at a time. So we're going to look at 2 compounds. We're going to look at calcium sulfate, and we're going to look at lead sulfate, lead 2 sulfate. So the equilibrium expression for calcium sulfate would be KSP equals concentration of calcium times concentration of sulfate. And so we can plug in our numbers. It gives us a KSP for calcium sulfate, 6.1 times 10 to the minus 5th. We know what calcium is, 0.010. And we want to know what the concentration of sulfate needs to be for this to precipitate. So our concentration of sulfate needed is 6.1 times 10 to the minus 3 molar. And this is how much is needed to precipitate calcium sulfate. And there's a reminder here, a precipitate will form when Q equals K. For the lead sulfate, we have the same idea, and the equilibrium expression is not all that different, other than including lead too. Their charges are equal in number, which means for every one lead, we have one sulfate. That makes equilibrium calculations pretty nice because there's no exponents other than 1. KSP for lead to sulfate is 1.3 times 10 to the minus 8th. We know the lead concentration was 0.010. And we are looking for the concentration of sulfate, meaning how much sulfate does it take for this lead sulfate to precipitate. And so let's solve for it, and we end up with 1.3 times 10 to the minus 6th molar, and this is how much is needed to precipitate lead to sulfate. No parentheses. So now we need to figure out which one is going to precipitate first. We know that calcium sulfate precipitates at this concentration. We know that lead sulfate precipitates at this concentration. So what this is telling us is that lead 2 sulfate requires less sulfate than calcium sulfate. So because lead sulfate requires less of the sulfate ion, it will precipitate first. So what happens is we're slowly adding sodium sulfate. Every time we add a little bit, we have to decide which one of these is going to take it and precipitate first. This one has the smaller solubility here, and so this one precipitates first, because for the calcium sulfate, it would still be aqueous if we added it. And so here it's aqueous, it finds a lead, it makes a precipitate. We put in a little more. It's dissolving as far as calcium sulfate is concerned, and so it finds a lead, it precipitates out. Eventually, when all of this lead is precipitated out, then we're adding sodium sulfate, and eventually we hit this point. And that is the point when calcium sulfate begins to precipitate. You could reword the question move this up a little bit. So rewording the question, what is the lead to concentration when calcium sulfate precipitates? Or what is the concentration of lead to when sulfate concentration is 6.1 times 10 to the minus 3 molar?